discussing about invert invert Z transform. Sorry. The last method, that is the residue method of computation, we will discuss today. X n, the sequence, is obtained by evaluating this integral z to the power n minus 1 x z dz. The contour C is taken to include all the poles of x z. You choose any contour which can include all the poles. So, x n can be written as, by Cauchy's theorem, sum of the residues of z to the power n minus 1 into x z at all the poles. Okay. And for multiple poles at a particular location, for multiple poles the residue is calculated. Residue f z at p k, where f z is this product, residues of say f z equal to z to the power n minus 1 into x z. So, residue of f z will be 1 by m minus 1 factorial d m minus 1 by d z m minus 1 z minus p k into f z, evaluated at z is equal to p k. Okay. Let us see this with an example, how this can be applied. Let us take x z, the same example, z inverse by 1 minus 0.25 z inverse minus 0.375 z to the power minus 2, which we took last time. So, this will be z by, I can write 1 minus z minus 0.75, these factors we got last time, z plus 0.5. Okay. So, f z will be z to the power n minus 1 into x z, which is z to the power n minus 1 into z, that will give me z to the power n by z minus 0.75 into z plus 0.5. Okay. So, you can evaluate x n by that method of residue. Once you have got f z, there are two poles, one at minus 0.5, the other one is at plus 0.5. So, evaluate it, it comes as x n. Okay, let me write the residues first. X n will be residue of the first pole that is z to the power n. If I multiply by the first pole, so z plus not 5 I get in the denominator. This is to be evaluated at z is equal to 0.75 plus residue. The second one is z to the power n by z minus 0.75 evaluated at z is equal to 0.5. Is that all right? Minus 0.5. Thank you. So, that gives me, if I put z is equal to 0.75, So, it will be 0.75 to the power n, okay. 0.75 will make it 1 by 0.5 plus 0.75, 1.25, and minus 0.5, and the denominator will be minus 1.25 in the second case, and minus 0.5 to the power n. So, whole thing multiplied by un will be xn. It is so simple. This is what we got by the other method. 1 by 1.25 was 0.8. So, I can take that as common. So, that gives you 0.8 into 0.75 to the power n minus 0.n un. Let us take another example with multiple roots. xz equal to z squared by z minus 0.5 into z minus 1 whole squared. Okay. So, you have to differentiate and then find out the residue. So, residue for the first part, before that let me compute fz, which will be z to the power n minus 1 into xz, which will be z to the power n plus 1 z square into z to the power n minus 1. All right. So, xn will be residue at the first pole, it will be z to the power n plus 1 by z minus 1 whole square 0.5 evaluated at this pole. This is the first one. Okay. I will call this as say x1, this will be 0.5 to the power n plus 1 by this is 0.5 minus 1. So, minus 0.5 squared. So, 0.52. So, that gives me okay 0.5 to the power n minus 1. I may write as 2 into 0.5 to the power n. If you permit me, I can write like this. Similarly, the second one I am writing separately x1 and x2 and then add them together. Is that all right? x2n for the second one, I will take residue fz at this pole, which will be, if you differentiate this one, it will be z to the power n plus 1 by z minus 0.5 d dz of this one, is it not? You have to multiply by z to the power z minus 1 whole squared and then calculate the function. Okay. So, that gives me z to the power okay n plus 1 into z to the power n into z minus 0.5 minus z to the power n plus 1 into z minus 0.5, the derivative is 1 divided by z minus 0.5 squared, and this is to be evaluated at z is equal to 1. So, that gives me, if you put 1 n plus 1 into 0.5 okay, n plus 1 into 0.5 minus 1 divided by 0.5 squared. So, that gives me 2 into n minus 1. Okay. Therefore, x n is 2 into n minus 1 plus 0.5 squared into u n. It was 2 sorry, to the power n, not square, sorry. Is that all right? This is to the power n x 1. Now, there are certain important properties of Z transform. Let me just list out some of them. We will take up one or two for proof. One is the very helpful linearity. A into x 1 n plus b into x 2 n gives me A into corresponding Z transforms x 1 z and x 2 z multiplied by A and B. Okay. This we also observed for frequency domain representation or frequency transform A into x 1 e to the power j omega plus b x 2 e to the power j omega. Okay. When we discussed about DTFT, discrete time Fourier transform, we will get back to that very soon. Then delay or shift, this also we observed earlier. If x n is having a transform x z, then x n minus say capital N will be z to the power minus n x z. Okay. Convolution y n, if it is convolved in the discrete time domain, x k and h k, if they are convolved, then in the frequency domain, in the z domain, there will be a product form. These proofs are very similar to Laplace transforms, where you have seen convolution, a delay, linearity, these are very simple relations. Differentiation, x n is x z, x n is paired with x z, then n times x n is minus z dx z by dz. Let us take up this one as an example. X n by definition is a sequence x 0, x 1 and so on. Okay. So, x z is x 0 plus x 1 z inverse and so on. All right. So, what is dx z by dz? It will be x 0, derivative is 0, then x 1 and z 1, if I take the derivative, it will be minus z to the power minus 2 plus minus z to the power minus 3 into 2 into x 2 and so on. If I take z to the power minus 1 common, it will be minus z to the power minus 1 minus z common, okay, sorry, z to the power minus 1 common, sorry, z to the power minus 1 common, it will be x 1 z to the power minus 1 plus 2 into x 2 z to the power minus 2, 3 into x 3 z to the power minus 3 and so on, which is nothing but z inverse. This is a z transform of what? N x n, is it not? As if 0 into x 0 plus 1 into x 1, 2 into x 2, 3 into x 3, these are appearing. The 0 term is missing because it is multiplied with 0. Okay. So, it is z transform of n times x n, this series. So, if I transfer this to this side, you get the result minus z into dxz by dz is equal to z transform of n x n. Okay. Then modulation, that is y n is x n into h n, all right. Then y z will be 1 by 2 pi j g v h z by v v to the power minus 1 dv. The ROC, region of convergence, includes RG and RH. Okay. We will be taking up some simple application of Z transform in real systems. Okay. Then we will go back to discrete time domain and frequency domain representation once again and try to find out a common link between Z transform and frequency domain transform. Okay. Say we are given x n as 0.5 to the power n u n, h n 0.2 to the power n minus 1 u n minus 1. What will be y n, which is convolution of x n and h n? Sometimes we use a circle around the star for denoting convolution, because star is quite often used for complex sequences, also complex conjugates. So, to avoid confusions, okay, we use this. So, let us use that relationship for convolution. Y z will be therefore x z into h z, and what is x z for this one? 1 by 1 minus 0.5 z inverse, is it not, for 0.5 to the power n, and h z, this is delayed by one step. So, it will be z to the power minus 1 and 0.2 to the power n, z transform is 0.2 z inverse. Is it all right? So, you know the product, make partial fractions. Okay. let me use this paper. Okay. So, y z is z to the power minus 1 by 0.3, 1 by 1 minus 0.5 z inverse minus 1 by 1 minus 0.2 z inverse. See, in such cases it is very simple. If you have the product like 1 by 1 minus a z inverse into 1 by 1 minus b z inverse, then you straight away take the partial fraction as 1 minus a z inverse minus 1 by 1 minus b z inverse. Okay. Ones will get cancelled. So, what you will be left with is a minus b in the numerator. So, divide by a minus b. That is what I have done. The difference between 0.5 and 0.2 is 0.3. So, I have divided by 0.3, and there was a z inverse in the numerator. So, I have taken it out. So, that is approximately 3.33 z inverse into this. So, what will be y k? It will be 3.33, or you can write 10 by 3, either way. Solution for this to be delayed by one step, inverse of this to be delayed by one step. So, this is 0.5 to the power n minus 1 u n minus 1 minus 0.2 to the power n minus 1 u n minus 1. Okay. So, this is the solution. Yes, please. Z inverse will come as n minus 1. Partial fractions, one will get cancelled. There is a Z inverse already coming in. So, this will not be there. So, thank you very much. So, I need not have a Z inverse. This itself will give me the Z inverse. Thank you. So, it will be just n, no, then 0.2 un. Yes, it will be, sorry, it will be this. Z inverse will automatically come from the subtraction. Now, let us take an interesting application, radar tracking system. In a radar tracking system, what you do, you have a source of signals, you are sending pulses, all right. Suppose you are tracking a moving object, all right. So, the pulses will be going at the velocity of light, of course, and then that will be reflected back. You are sensing the reflected signal, you are finding out the time delay, that divided by 2 will be giving me the distance of the object, all right. Now, you keep on measuring it, all right. So, if you are sending signals at regular intervals and receiving signals at regular intervals, then you try to compute, you try to estimate its position and also its velocity. If you know its position at a certain instant of time and its velocity, you can predict after say 1 second what will be its possible location. You know its direction, velocity and position. So, you know its direction. So, along that direction, you know after 1 second it will be in this position. So, you fire the next shot, all right. You fire the shots to the object, to the enemy object, you know the velocity of the missile, and then you can destroy that. Okay, that is the idea. So, let us see a very simple mathematical model for a radar tracking system. So, I will show you a very simple schematic diagram. So, this is an enemy plane and this is a radar. So, you are sending a signal, this is object, c meters per second is the velocity of light, the signal is sent and you are sending the pulses like this. So, this is T. At regular intervals, all right. The received signal ideally at any instant, this is delta t, this is the received signal. Of course, this delta t will keep on changing because it is changing its position. So, the received signal, the time taken by the pulse to return back will not be same throughout, that is changing. So, this gap is changing, okay. But the actual signal is contaminated. The received signal, actual received signal will be somewhat like this. So, there is a threshold that we take and this is our actual time we are counting, okay. It will be contaminated by noise and there is a filtering effect of the space. So, this is the actual received signal and this is the ideal received signal, this is the sending pulses. Let us take xk as the measurement of the range, from the kth pulse. Okay. So, what will be xk? It will be delta tk by 2, delta tk is the time for the kth pulse to return, all right. So, delta tk by 2 into the velocity of light, so many meters, okay. Yk is the estimate of the range after processing kth pulse. Okay. That means, when I ask you to make a measurement does not give you any measurement for that matter, measurement does not give you the exact value. For example, in your high school physics experiments or even here, you take a measurement 10 times and then take the flat average sometimes, all right. In schools you are you learn to take only the arithmetic average. Later on you must have observed you take the most probable value, that means the value which is occurring more often is taken as the estimate. You can always make an estimate. Now, there will be always some measurement error, all right, personal error and so on. So, instrumental error. So, depending on the complexity of the experiment, you make an estimate of any item, any variable from the set of measurement. Okay. Then Vk is the estimate of the object's velocity. and ypk is the prediction of the object's range. Whenever you are making a prediction, prediction is based on the previous measurements, all right. So, after processing k minus 1th pulse. So, on the basis of k minus 1 readings, you make a forecast, you make a prediction what will be its position at the kth instant, and you have made an actual measurement. So, that gives you an error, prediction error. So, you take that error as a feedback, and let us see how these estimates are modified with the help of that feedback. So, ypk, the predicted value, how much is the predicted value? Say up to this instant of time, I have got yk minus 1 as the estimate. What will be my prediction in the next instant? If I know its velocity, if I have an estimate of its velocity, then velocity multiplied by that time gap, capital T, that we are considering. So, multiplied by that time gap will be the additional increase in the range. So, T into y v k minus 1. Suppose this is the k minus 1th instant. So, at k minus 1th instant, if I have estimated the value of the velocity of the object, if I multiply by the time interval, I will get the increase in the value delta y. Okay. So, that multiplied by the present estimate, that will be giving me the prediction. Similarly, yk, what will be the estimate at the next instant, that is after processing k number of measurements, what will be its value yk. How will you estimate what is yk? It is the predicted value, whatever was predicted to be the value at this moment from the previous instant, yp k minus 1, plus we take a correction factor into the error, all right. And what is the error? Measurement, I am using third bracket. So, let me be consistent, minus is that all right? This was the prediction error. So, prediction error multiplied by a constant, normally less than 1, plus the prediction made in the previous instant. It should be, prediction is made at this instant, mind you, prediction is made at this instant from the previous data. This is prediction error. Okay. And yvk, what will be the estimate of the velocity? It will be whatever velocity was estimated in the previous instant plus the prediction error. From that prediction error, I will estimate the prediction error in velocity. So, beta times 1 by t times the same prediction error. Is that all right? Whatever is the error in the position, that divided by that time t gives me error in the estimate of the velocity. So, that multiplied by a factor beta, if I add with the previous estimate of the velocity, that will give me the present estimate of the velocity. Okay. This is known as an alpha beta tracker. Now, let us take Z transform of these. So, from here, if you permit me, these three equations I will write for, say, for example, the second equation. What will be the Z transform of this? Y z is equal to y p z plus alpha times x k minus 1. So, x z into z inverse minus y p z. Is that all right? Similarly, first equation here will give me y p z. Okay, let me arrange these. It will be y z minus y p z into 1 minus alpha. Okay. Is this all right? Y p z, this one, okay. On this side, alpha z inverse x z. Is that so? Is this all right? Next one, y p k is equal to y k minus 1 plus t y v k minus 1. So, if I take the Z transform, y p z equal to Z inverse y z plus t Z inverse y v z, or in other words Z inverse into y z minus Z inverse into y z minus y p z plus t Z inverse y v z equal to 0. And the third equation, this one, gives me y v z, okay, equal to Z inverse y v z plus beta by t Z inverse x z minus y p z, or in other words I can write 0 into y z, there is no y z term here, okay, plus beta by t y p z plus 1 minus Z inverse into y v z is equal to beta by t Z inverse x z. This is equation 3. I have tried to arrange the three equations in such a way that you can write a very simple form, a matrix equation. I would request you to fill up the blanks. Y z, y v z, y p z and y v z will give you something into x z. These elements you fill up from these equations. So, it is a very simple matrix equation. You can find out y z by x z, you can find out y v z by x z, you can find out y p z by x z. Try it at home. What will be the transfer functions? That means the input signals, the input measurements from the measurements, not from the signals, mind you. Xz is a measurement. So, with the measurement, how are you making estimates of the velocities, position and the prediction. Okay. Now, if you have a general equation of this type, say A0 yk plus A1 yk minus 1 plus A2 yk minus 2 and so on up to An yk minus n. On this side you have B0 xk plus B1 x k minus 1 and so on up to Bm x k minus m. This is obtained, this is a generalized form of a difference equation obtained from differential equation. Once earlier we have discussed how from a differential equation you can approximate and you can make certain approximations about the derivatives and you can get a difference equation. Now, difference equations will not be identical for the same differential equation if you change the step length, if you, because there are factors t squared, t cubed depending on the order of the derivatives. So, it all depends on the step length, that is the sampling time that you choose. Okay. If you change the sampling time, the difference equation coefficients will also be different. Okay. This is something very important. Now, such difference equations can be converted into can be converted in the z domain. So, we get a transformed equation. So, you get A0 yz, if you assume 0 initial conditions to start with, it will be z inverse yz An z to the power minus n yz, it will be B0 xz plus B1 z inverse xz and so on up to Bm z to the power minus m xz. I can take yz common, similarly on this side I can take xz common, and y by x will be B0 plus B1 z inverse Bm z to the power minus m divided by A0 plus A1 z inverse and so on An z to the power minus n. We call this as transfer function in the discrete domain. As you have done in the continuous domain, Laplace transform you take and then take the ratio of the output by input. So, this is the transfer function in the discrete domain. Given a transfer function, we can find out its impulse response. Just take the Laplace the z inverse of this, and you have seen for calculating z inverse there are 3 methods. You can use any one of them. So, you make factors, find out the factors, factorizing this and then making partial fractions, either calculate the residue or by the partial fraction method you can find out the solution, otherwise by long division you can calculate hk. So, this is normally written as hz or gz. Now, let us come back to discrete domain functions once again before we go further, because we will be requiring the discrete domain descriptions, especially in the frequency domain, and like the properties that we just now discussed in the Z domain, you have also in the frequency domain similar properties, that is some of them probably we discussed earlier. Linearity, the same principle, A times x1 n plus B times x2 n will give you A times x1 e to the power j omega plus B times x2 e to the power j omega, probably we mentioned it earlier. Delay or shift are very similar to Z transforms. Then your convolution, that will also be similar. Now, for convolution, suppose you have output y is convolved with x and h. So, it will be in the frequency domain x e to the power j omega, h e to the power j omega. If you can find out the values, it is okay. If you can get an analytical expression, and if you can take the inverse, so we calculate x e to the power j omega and h e to the power j omega. All right. So, if you are given a sequence xn as x0, x1, etc. So, calculate x0 plus x1 e to the power minus j omega and so on. If it is a mathematical description that is given, and if you can find the convergence, if you can reduce it to a closed form, say like if the sequence is 2 to the say 0.2 to the power n un, then you know the sequence is 1, 0.2, 0.04 and so on. So, you can write the expression, since it is a convergent series, you will be getting the solution very identical to Z transform. X e to the power j omega will be 1 by 1 minus 0.2 e to the power minus j omega. All right. This kind of a series, if you take the discrete time Fourier transform, all right. So, the frequency domain description of this sequence will be this. It is a GP series, I have reduced it. Since e to the power j omega is always having a magnitude 1, so 0.2 times this will not blow up, it will be a convergent series, okay, because the magnitude is reducing. All right. So, from here, if you similarly get e to the power h e to the power j omega in such a form, closed form, then take the product and then take the inverse. How do you compute the inverse? How do you compute the inverse? In your classical Fourier series, you have seen a periodic function, any periodic function, say this is a periodic function in the time domain, can be expressed in the frequency domain, as A0, okay, I will write in a complex form, Cn e to the power j omega n summation, all right, okay, plus n varying from minus infinity to plus infinity. If you combine together and then write in the complex form, it will be like this, okay. So, Cn e to the power j omega n, and we get lines, these are called harmonics, okay. I can just number them n, harmonic number 1, 2, 3, 4 and so on. These are the frequencies present. Now, what is the frequency transform of this sequence x0, x1, x2? What is the frequency transform? x0 plus x1, and this we saw earlier, this is a periodic function, all right, of period 2 pi, is it not? We discussed earlier, this is having a periodicity of 2 pi. So, if I now take omega and x e to the power j omega, you take its magnitude as well as phase, either way it is a periodic function, maybe like this, and this is 2 pi, minus pi to plus pi, 2 pi, then 4 pi and so on. So, it is a periodic function. In the time domain, if it is a periodic function, then in the frequency domain it is discrete lines, is it not? So, you just stretch your imagination. In the frequency domain, if it is periodic, then what is it in the time domain? It will be lines, and precisely that is what we have started with. It was xn, is it not? All right. How did you compute these magnitudes in the normal Fourier series? You integrate, say, a0s and b, say ai's and bi's. How did you compute? Or complex Cn? Integration over one period, then the function ft, then e to the power plus j omega n t dt. Was it plus or minus? Minus. Okay. So, in the time domain, if it is periodic, the corresponding frequency domain constants are evaluated from here, divided by t. Okay. In this case, by the same argument, I can evaluate xn. What is the periodicity? 2 pi, 1 by 2 pi, minus pi to plus pi, okay, x e to the power j omega, e to the power, now I will take plus j omega n d omega, okay, that will give me xn. So, once you have got you have got x and h, and if they are convolved in the time domain, so in the frequency domain you have to just take their products to calculate the output and then take inverse of that product, and for taking the inverse we will resort to this expression. So, our yn will be 1 by 2 pi minus pi to plus pi, product of x into h all right. So, given the two sequences, take the frequency domain transform, take the product, then take the inverse, that is integration over a period 2 pi after multiplying by e to the power j omega n. Okay. So, we will stop here for today and we will continue further in the next class. Thank you very much.